Hi, I'm Brian Freer, tutoring high school physics. Today's topic, linear momentum and collisions. So any object that is moving some direction in a straight line has linear momentum, and that's defined as mass times velocity, and it's represented by a lowercase p. Let's start out with this object, 5 kilograms traveling with a velocity of 5 meters per second. What's its linear momentum? Well, p equals our mass of 5 kilograms times our velocity of 5 meters per second. 5 times 5 is 25 kilograms times meters per second. We don't actually have any fancy units for this, it's just kilograms times meters per second. So the fun stuff in physics, though, happens when things bump into each other, and we end up with collisions. There are two big major types, elastic collisions and inelastic collisions. In elastic collisions, the objects will bounce off each other. In inelastic collisions, they'll stick together. They do have one thing in common, though, and that's the law of conservation of linear momentum. This basically says that the total momentum of all your objects before your collision is the same as the total momentum of all your objects after the collision. The difference in numbers, though, between elastic and inelastic collisions is that in elastic collisions, the total kinetic energy stays constant both before and after the collision. In inelastic collisions, this is not true. So let's work with an inelastic collision. Back to our object up here, let's say it collides with yet another object, and this one is also 5 kilograms. Let's write out our momentum equations. I'm going to use little letters for this one and big ones for here. So our total momentum before, so we have the momentum of this object plus the momentum of that object over here equals, now these are going to stick together to form one big object, so we're going to add the masses together, like so, times some new velocity v prime. Now that apostrophe just means prime, some other value for that particular measure. So now we can substitute in our figures. We have 5 kilograms times 5 meters per second. Now I actually notice that the second object has a velocity of 0 meters per second, so that entire part of the equation is just going to go to 0. So we can omit that. Equals the sum of our masses, 5 kilograms plus 5 kilograms times v prime. So let's start simplifying. 5 times 5 is 25 meters per second times kilograms equals 5 plus 5, 10 kilograms times v prime. We can divide both sides by 10 kilograms, and we get v prime is equal to 2.5 meters per second. Okay, so what about elastic collisions? Let's move on to that. We have two objects, and they're hurtling towards each other. One is 5 kilograms, hurtling at 5 meters per second. The other one is 4 kilograms, hurtling at 6 meters per second. So let's write out, again, our momentum equations. I'm going to use little letters for this one and big letters for that one. So we have mv plus big M, big V equals little m v prime plus big M v prime. Okay, so now that we substitute in our figures, we have a mass of 5 kilograms times a velocity of 5 meters per second plus a mass of 4 kilograms times a velocity of negative 6 meters per second. Notice that we define the velocity this way as positive, so the opposite way has to be negative. Keep in mind your signs for your momentum equations. They will be important. Equals our mass of 5 kilograms times an unknown velocity plus our mass of 4 kilograms times another unknown velocity. Okay, well let's start simplifying this out. 5 times 5 is 25 kilograms times meters per second plus negative 24 kilograms times meters per second equals, I'm actually going to start omitting units, but just remember what they are. I've written them down up here. 5v prime plus 4v prime. So now we finish this off. We get 1 kilogram times meters per second equals 5 little v prime plus 4 big V prime. Okay, problem. We have one equation and two variables. We can't solve this. But actually, since this is an elastic collision, we know that the kinetic energy is the same. So we can write out some kinetic energy equations. So for this one, we have 1/2 little mv squared plus the 1/2 big M v squared equals, and so the velocities will change, 1/2 mv prime squared plus 1/2 big M big V prime squared. So now we can substitute in our figures. 1/2 5 kilograms times 5 meters per second squared plus 1/2 times 4 kilograms times negative 6 meters per second squared. The negative doesn't matter so much in the kinetic energy equations because you're just going to square the value anyway, it'll become positive. Equals 1/2 times 5 kilograms times our v prime squared plus 1/2 times 4 kilograms times our big V prime squared. Okay, so now let's start simplifying these things. 5 meters per second squared is 25 times 5 kilograms gives us 125 kilograms times meters squared. But we're also going to have that, which brings us down to 62.5. I'm going to start omitting the units from these as well. Just keep in mind these are kilograms times meters squared per second squared plus So 1 half times 4 is 2, and 2 times negative 6 squared, well, negative 6 squared is 36. And so we multiply that by 2, we get 72, equals 1 half times 5 kilograms is 2.5 kilograms times v prime squared, plus 1 half times 4 kilograms is 2 times big V prime squared. And so we just add this together, we have 134.5, and keep in mind that's kilograms times meters squared per second squared equals this thing. Okay, so now we can actually start solving some of this. Let's first find out what a big V prime is. So we go back here and we can subtract the 5 V prime, the small v prime, from both sides, and then divide by 4. So we get big V prime is equal to 1 minus 5 little v prime over 4. Okay, now we're going to take that and substitute that in down here. So 134.5 equals 2.5 little v prime squared plus 2 times, oh dear, 1 minus 5 little v prime over 4, and this entire thing's squared. Okay, well, let's start working this out. 4 squared is 16, that's the easy part, but we're also going to multiply this entire thing by 2, so that's actually going to turn out to be 8. Because 2 over 16 is just 1 over 8, so that just goes to 8. And we're going to do some FOIL up here. We have 1 minus 10 little v prime plus 25 v prime squared. And so we still have the rest of this equation, don't forget that, equals 2.5 v prime squared plus this. Okay, so now we multiply everything in this equation by 8 to get rid of this here denominator, and we'll end up with 1076, and remember the units on this is kilograms times meters squared per second squared, equals, well, if we actually put all these terms together, we'll get 45 v prime squared minus 10 v prime, and I believe that's, yes, plus 1. Okay, so now we subtract the 1076 from both sides, so we get a quadratic. 45 v prime squared minus 10 v prime minus 1075 equals 0. And so now this is very easy to punch into your quadratic formula, and we'll end up with two answers for v prime, and they are 5 meters per second and negative 4.78 meters per second. So which one of these do we want? Well, if our v prime is going to be 5 meters per second, it's going to be the exact same as what we have up here. And that makes no sense. When two objects hit each other, they tend to go opposite ways to the way they were originally traveling. So we'll actually want the negative value, negative 4.78 meters per second. But that's only one of the velocities. We'll need the other one. So we go all the way back here, and we have 1 kilogram meters per second equals 5 times our newly found negative 4.78 meters per second, plus our 4 times our big V prime. Okay, so now we do a bit of math, and we'll come up with 1 equals negative 23.89 meters per second plus 4 times V prime. So we add 23.89 meters per second to both sides, and we'll end up with 24.89 meters per second on this side equals 4 times V prime divided by 4, and we get a final velocity of 6.22 meters per second for this object. Alright, to recap. Any object that is traveling in a straight line has linear momentum. We show that by a lowercase p, and that's equal to mass times velocity. The units you're going to get are kilograms times meters per second, no fancy units on this one. There are two different types of collisions, elastic and inelastic. In elastic collisions, the objects will bounce off and the total kinetic energy is conserved, the same before and after the collision. In inelastic collisions, the total kinetic energy is not conserved, so don't even write out equations for that. However, one thing is the same, and this is the law of conservation of linear momentum. Regardless of the collision, the total momentum of all the objects before the collision is the same as the total momentum of all the objects after the collision. Alright, that's all for now. Again, I'm Brian Freer. See you next time.